speakers that the talk would be 25 minutes talk plus 5 minutes Q&A. And okay, so now let's welcome our first speaker, Professor Tony Heinz from Stanford University and SLAC National Accelerator Lab. Professor Heinz, please.
Thank you very much, Zhenglu. Thank you, Steve. I'm really delighted to have a chance to participate in this nice event that I have to say lies extremely near and dear to my heart. You know, working on optical properties of materials, the advances in theory have been absolutely essential and things we've been doing over the years, and collaborations with people involved in this conference have really aided us a lot. I'd like to concentrate on a recent experimental advance in the field of 2D materials, which is the use of photoemission spectroscopy. And of course, that probably sounds like a little standard technique, but photoemission spectroscopy on photoexcited systems. So trying to look through photoemission techniques at excitons in 2D materials. This has been a broad collaboration. As you'll see, theory has played an essential role. But I should say from the fundamental experimental point of view, it wouldn't have happened without the interaction with Keshav Dani's group at OIST in Japan. So what I'd like to tell you about is just a few basic things about excitons in 2D materials. For those of you who are not so familiar with this very active subfield, but mostly then focus on how we use ARPAs, but in this time-resolved mode on photoexcited systems. And I'll tell you about some work we've done looking at monolayers by themselves. First, just looking broadly at the momentum distribution of excitons, and then a little more specifically at the momentum character of a given exciton. And then a little bit about some very, very recent work still in press on applying this technique to heterostructures. So these are our favorite materials here that you're probably all pretty familiar with, the 2H phase monolayers of the transition metal dichalcogenides, moly sulfide and tungsten sulfide, tungsten selenide being prototypical examples. Interest is focused a lot on the band structure near the corners of the Brillouin zone. They're basically you know, parabolic bands, but you have interesting chiral selection rules associated with the valley circular dichroism indicated here. That's what I'm not going to talk about so much now, but the other essential effect in these 2D materials, because of the reduced dielectric screening, are the very, very prominent excitonic effects. Just by way of history, I go back to one of our old spectra, but one of my favorites. This is monolayer tungsten sulfide. And you see this absolutely huge peak associated with band edge transitions. And of course, as you know, if you had uncorrelated transitions, you'd get something close to a step function, and you see this huge peak associated with the excitonic character. This is then the next higher lying state associated with the split off valence band. And this is the spin orbit splitting in the valence band in the system. So basically the low energy excitations are dominated by these excitonic features. And you know, there's been a huge effort in this theoretically and experimentally. One of the next experimental steps was the ability to identify some of the Rydberg excited states here. And this is plotting up some of those states. And what you can infer from this immediately, just looking at this progression, is the energy between the continuum limit and the strong 1s ground state. The exciton binding energy is very large in these systems, hundreds of millielectron volts. And you know, that was something that was ab initio calculations. This is more of a model calculation, just fitting this excited state spectrum to this screened Keldysh potential as model potential. But it shows both the high binding energy and, of course, the unique kind of screening environment you have in a 2D layer. Just to give you a little more of a physical picture, this is a corresponding excitonic wave function. So it's, of course, quite small because of the high binding energy, but it's still in this Wannier limit. It's not localized on a given site. So you can think of it in, you know, described in that, that limit. but having a sufficiently high binding energy that really dominates the optical properties and even completely defines the optical properties at room temperature, which often is not the case for excitonic effects. So that's just a very little brief summary. And to bring you a little more to the state of the art in the spectroscopy, with advances in the material quality, and particularly with the realization that a homogeneous dielectric environment is crucial, and corresponding development of more nitride encapsulation techniques, we get much sharper lines, with reduced inhomogeneous broadening. And you start seeing, a very fascinating array of different higher order excitons. So these would all be sort of the substructure of that A exciton, that spectral range that I showed you before. So we have neutral excitons. We also have clearly defined different charged excitonic states, higher density of biexcitons, charged biexcitons, and also some spin forbidden transitions. So, on the one hand, we're really getting a much more detailed picture of what's going on. On the other hand, I should point out, limitations of optical spectroscopy, which is if you don't have something that will help you with momentum conservation, you miss a lot of the excitons. So we're basically, in absorption spectroscopy, we essentially see excitons that involve the direct transition. And even then, only the excitons that have a small center of mass motion, so they can couple to a photon. So those are the ones lying within the light cone. But if you look more broadly, there are actually quite a number of different types of dark excitonic states. There are ones associated with this somewhat smaller splitting in the conduction band that give rise to actually a pair of bright and dark triplet and singlet-like excitons in this region. Then there are also other valleys in the band structure that can give rise to excitons that have a significant amount of momentum and won't be seen optically without the intervention of defects or phonons. So there are actually quite a few excitons that are a little bit hard to identify or somewhat indirect, require indirect identification through the conventional optical spectroscopy techniques. Just by way of an example of the importance, if you look at the efficiency of photoluminescence in two of these monolayers as a function of temperature, going down from room temperature, in the tungsten selenide, you see a big decrease in the photoluminescence efficiency. In moly sulfide, you see conversely a big increase. So actually the big increase is what you might expect, because more of the excitons will lie in the light cone at lower temperature. The big decrease is something that we used as evidence for the existence of a lower lying dark state, which was this spin forbidden state that had been predicted. But of course, that's very indirect, and you could be fooled if you had a lot of defects that trap the excitons. In this particular case, in some work jointly with Steve's group, we took advantage of their very clever idea of putting an in-plane magnetic field to brighten the otherwise spin disallowed dark exciton states, and we're actually able to see both the dark and bright excitons. But this shows you some of the experimental challenges in identifying excitons other than the subset of bright excitons associated with spin allowed direct transitions within the light cone. So if you ask then, are there ways we can see excitons more generally across momentum space? The answer that naturally comes to mind is a technique that's used to characterize band structure generally. And that is using light to photoemit electrons and then resolving the energy and momentum of the photoemitted electrons. So that's the ARPAS technique. However, we need to augment that by doing it in a time resolved way, because you usually can't generate a high enough density of excitons in steady state to expect to apply this technique broadly. So you actually want to use pulse excitation, and then you photoemit shortly after that. And this also has the merit that it provides a very nice way of looking at dynamics across the band structure. So what can you get from this? Well, you can get a more comprehensive view of bright and dark excitons. You immediately see their valley character. You can infer information about the dynamics. And I think something that's interesting and important and distinctive, although perhaps at pushing the experimental limits is really imaging the excitonic wave function in momentum space. You'll see what I'm talking about in just a moment. Of course, this is a conventional ARPAS concept that you know. You have a photoexcitation with a photon energy well above the work function, and then you resolve the energy and momentum of the electrons. This is typically implemented in the conventional way using synchrotrons now, but for this time resolved technique, you need a short pulse, so that's really been driven by using pulse laser excitation. The tricky thing is you need a pretty high energy photon here to do the photoemission spectroscopy well. So this is just a schematic of the apparatus that was developed by Keshav Dane's group. What I should stress is technically it's pretty difficult because you want these higher energy photons, so that involves amplifying pulses to high energy and doing high harmonic generation. Ideally, to get to see the whole Brillouin zone, you want something like 20 eV photons. Then you'd like to have the time resolution, which means you do it with ultra short pulses. But in addition, for 2D materials, it's good to have an apparatus that can operate with a fairly small spot size. You can look at things like heterostructures that maybe you can't fabricate over very large areas. So this particular setup that Keshav has developed fulfills all of these different criteria. There is a hardy band of a few other groups who I've listed here who are applying similar techniques, and there are a lot of exciting results just coming to the fore now. So let me go right to the results here. These are some of the parameters just to give you an idea experimentally. We get something like 100 femtosecond time resolution, 30 MeV energy resolution, 0.01 inverse angstroms momentum resolution. A critical thing for people more experimentally oriented is this is done at a high repetition rate, which allows you to get high quality data. So this is just applying, the figure you see here is applying the apparatus to an unexcited sample. And this is actually very similar to nice spectroscopic data in ARPAS that is obtained, for example, at the ALS beamline with the micro and nano ARPAS. So you do resolve all of the filled bands and valence bands and higher valence bands and lower line valence bands. The dotted lines are a fit to a theory. You get strong matrix elements and density of states. You get very strong emission at the zone center here. And then these are the signals associated with the K-valley, two sides of the Brillouin zone. So the dotted lines here are a calculation by Ting Cao, actually, of the excited state structure. So those, of course, you don't see experimentally without any, you see no trace of them without any kind of excitation, since there are no electrons in those states. Okay, then the excitement begins when we shine a laser and we photoexcite. And what we do for the simplest measurement is we resonantly create one of those A excitons that I showed you before. So that means actually exciting with an energy that lies below the quasi-particle band gap by the exciton binding energy, 300 millivolts or so. And we know exactly where to excite from the absorption spectra. So we do this, and what happens? Well, we see a very nice signature of a new photo-emitted electrons. And one of the interesting things is allowing a little bit of time to lapse after photoexcitation. We see electrons that were created by the direct transition of absorbing the exciton to the K-valley, but we also see excitons or electrons that are associated with the this valley lying in between the zone center and the K-valley, designated here as the Q point. So we immediately see a signature both of this bright exciton and a momentum forbidden dark exciton that you would not easily see in a conventional optics measurement. We can learn about the dynamics when we do resonant photoexcitation. We know we're not going to be creating these excitons associated with the Q valley. So we can track the evolution of the signal, how it builds up both in the K valley and in the Q valley. And when we do this, we see within our time resolution a clear delay in the emergence of the signal in the Q valley. So that's a delay on the order of 100 femtoseconds, and that corresponds to the inner valley scattering time. It's sort of at the resolution of our experimental technique, so it's hard to pin down a very specific number. But you can clearly see that there is a delay, and this is exactly what you expect because you need interaction of exciton phonon scattering to get the exciton from the initially created K valley to the Q valley. So I should say this is pretty compatible with some theoretical predictions, but from the point of view of experimental signatures, we were often dealing with much more indirect evidence, as I'll show you in a minute. I just want to show you here some other recent data by a group in Marburg that replicates exactly this kind of thing with even slightly higher time resolution, and actually can, I think, begin to extract very precise state-specific exciton phonon scattering strengths. That's the kind of information you get naturally out of these kinds of data. I was going to say that, you know, how do we try to infer these things before? This is an experimental measurement where we looked at the line width of the K exciton as a function of temperature. So what happens is you have a relatively narrow line, really dominated by sample quality and radiative rates at low temperature. And then as the temperature goes up, you open scattering channels and the exciton line width increases. And this was some kind of analysis that tried to break this down into different scattering channels. And the one that was believed to increase the most was actually this inner valley scattering process indicated here. But of course, you can understand this is very, very indirect kind of evidence, and a completely different thermally activated scattering channel might have replicated the experimental data. More recently, we had something that we thought was a little more specific when we looked at the exciton line width under strain, and that actually is known to change the relative disposition of the two valleys, and we saw a signature of turning on the scattering channel by this means. So it's quite consistent with what was known before, but you know, it's very satisfying to have such a direct and unambiguous signature of these dark excitons, and also be able to look at the exciton phonon scattering rate directly in the time domain. Let me come to a more basic issue, though. You might say this is all very nice, but Tony, how do you really know you're looking at excitons? Maybe you're actually creating uncorrelated electron hole pairs. Well, let me kind of walk you through the process, and you'll see there's a very clear experimental signature for looking at photoemission from excitons as opposed to looking at photoemission from photo-generated uncorrelated carriers. So in our experiment, we use a resonant pump and we create this excitonic state. And that state that we create is going to be this correlated superposition of an electron state and a hole state connected by the excitonic wave function. So if we actually create resonant excitation, it's going to be stationary or nearly stationary within the light cone. So we'll create a state like this. That's what we initially have. Then we ask what happens when you come in with a high energy photon. Well, you project out a component of the electron and turn it through absorption of a photon into an electron in free space, leaving the sample. And if you detect an electron with no momentum, then by momentum conservation, what you're going to leave behind is a hole that also has no momentum, right? You'll project out that component of the wave function. So then you'll get an electron, and its energy should be defined by the energy that you put in the system by creating the exciton. So it actually won't be at the band edge, but it'll be lowered by the exciton binding energy. Well, that would be one signature, but the truth is we don't know experimentally exactly where the quasi-particles lie. That's something that potentially could be addressed by doping the sample, but that's technically somewhat difficult. So there's a shift, but you know, that's not, as it happens, a very direct experimental signature. However, let's consider the dispersion of these photoemitted electrons. So when you just carry out the same argument and consider the defined initial state of the exciton and the creation of a photoemitted electron at a finite momentum, the conclusion is that you'll see a dispersion relation that's inverted. It doesn't mirror the conduction band. It actually replicates the valence band. And the reason for that is when you project out a component of the excitonic wave function with a finite momentum for the electron, you have to leave behind a hole also with a finite amount of energy. So it's a necessary consequence of having a well-defined excitonic state that you actually get an inverted dispersion relation from what you get from photo-generated free carriers in the system. And in fact, that's indeed what we see. One sees only a limited part of the dispersion relation, but it's very clearly sloping down. Also, because of the quite large binding energy in this, we are confident that it lies well below the energy that you get from the emission from a free particle in the conduction band. But the inverted dispersion relation is really one of the interesting results. Going a little more into the details, there is also a very important experimental signature of the character of the exciton itself. So in sort of the broad overview, we could say the electrons come out with momentum more or less corresponding to the K valley, or they come out with a momentum corresponding to the Q valley. But if we just look at one of those excitons, for the reasons I just discussed, since the exciton itself is this coherent superposition